Well, the clock is broken, doesn't work, so I'll have to use the one on my phone. Anyhow, well, let's remember where we stopped, what we did last week, and where we stopped. Last week we proved that a spectrum is dualizable. Which is equivalent to requiring the spectrum to be the suspension spectrum of a finite CW complex with possibly with a shift. And we know if an object is dualizable, then the dual the dual should be the internal Hom into the monoidal unit. Very well. But we want to describe this dx more explicitly, because in general those Homs into the unit are difficult to get the handle on. So we started proving we started proving the following thing. Suppose K is a finite CW complex which is inside Sn, some sphere. Then we want to show that D, the dual of the suspension spectrum, is the suspension spectrum of the complement with a shift, minus n minus 1, minus n minus 1. So this is what we wanted to prove, and we almost proved it. Let's try to remember what we did and didn't prove. we did construct a map. In which direction? Does anyone remember? Okay, so we did construct a map. Well, let's denote this A. To the dual spectrum, and we proved a few things about this map. Firstly, we observed that by construction the map is functorial with respect to inclusions of complexes and secondly the map is independent of the embedding, and let's recall that the way to prove independence is as follows. Suppose we have X inside Sn. Let's increase the dimension n by embedding Sn in Sn plus 1 as the equatorial sphere. Then well, X will K will be embedded in Sn plus 1, and A will get replaced with the suspension of A. So the complements are different, no question, but the suspension spectra are the same. So if we change n to n plus 1, x remains the same, dx also remains the same, and what happens on this end? On this end, n minus 1 becomes n, and a gets replaced with a suspension of a. So we get the same spectrum on the left. Andrei, does any of this make any sense? Very well. Despite the fact that we use the embedding to construct a map on the level of the homotypic category of spectra. The result does not depend on the embedding. Very well. Well, it remains to prove that this map is an isomorphism. And we well, to prove that the map is indeed an isomorphism, we assume that X is a subpolyhedron up to homotype equivalence. It doesn't matter whether we consider finite polyhedra or finite CW complexes. And we well, we start with, well, to begin with, we need the base case when X is a point. Well, if X is a point, then the basically everything else is a point, because the dx and the a so we get basically in both sides we get the zero spectrum, and there's a unique map between the zero spectrum and itself, and it's an isomorphism. So after this we add phases one by one, and we want to use the cofibration sequence on the left, and the same and a different cofibration sequence on the right. So let me think how to. Okay, so. Okay, so. Suppose we have X, which contains Y, and or okay, since I have since I'm using K for since I'm using K for the complex and X for the suspension spectrum, let me keep doing that. So suppose we have two subpolyhedra, and the statement is the map is an isomorphism for the suspension spectra of these polyhedra. Now let me glue a cell, or more precisely, let me glue the cone over L to this thing, and I view the result is embedded in Sn plus 1. Okay, so here's the picture. Does the picture make sense? Very well. So we want to prove that the for n plus 1 we also for this polyhedron we also have an isomorphism. Okay, so we have the following sequence of polyhedra. Okay, so firstly, I take Sm plus 1 minus the suspension of L. Which is the same as after homotopy as Sm minus L. Does everyone agree? And this is the smallest complement. Well, the next smallest complement is the one we're interested in. Then I have Sn plus 1 minus k and Sn plus 1 minus L. The smaller the space, the bigger the complement, and vice versa. Well, this thing is the same as the suspension of Sn minus k, and this is the suspension of Sn minus L. Well, technically, the embeddings here are open embeddings, but we can always replace all participating spaces by subpolyhedra, and up to homotopy equivalence we get the same thing. Okay, so does this sequence make any sense? So I claim this is part of the cofibration sequence. Of the first error. Again, up to homotopy equivalence. Well, so what do we do with it? Well, we observe the following thing. Well, firstly, we can recall that sigma infinity, the suspension spectrum functor, preserves cofibration sequences, and so the resulting sequence of spectra is a cofibration sequence, and and secondly, the D also the dualization functor also takes go vibration sequences to go vibration sequences. Okay, so we have one go vibration sequence on the left, and another one on the right, and since all maps in the go vibration sequences are induced by inclusions of subpolyhedra, we get the following thing. So we get the following commutative diagram. Sn plus 1 minus sigma L. I will just write the spaces, and I will add the suspension functor later. So Sn plus 1 minus KCL, Sn plus 1 minus K, Sn plus 1 minus L. Okay, so this is what happens for spaces, and for spectra, I just add sigma infinity everywhere. Okay. This goes into dx. With okay, let me also add shifts. Okay, so the shift is minus the dimension of the sphere minus 1. The dimension of the big sphere is n. So well, I add minus n's everywhere. Okay, so this goes into dx. No, this goes into dy. This goes into well, let's call this z. So this will be dz. dz, and this will be dx. Actually, let me slightly change the whole thing. So here we have sigma infinity minus n as n plus 1 minus k. But this is the same as sigma infinity minus n minus 1 of Sn minus k. I'm running out of space. Okay, so let me erase this thing and just add shifts here. What should I put? Minus 1 and 1. Okay, so this thing is the suspension of the so what did you say? Let's say it says 1, and well, I agree, but nevertheless. Please, everyone check this for yourself because I've been known to make this type of mistakes. Okay, so the important thing, we have two cofibration sequences on of spectra so we have a map of two cofibration sequences. And now we want to show that the arrow in the middle is an isomorphism, and the easiest thing to do would be to pass to the homotopy groups of both both sequences, which gives us a long exact sequence on at the top, another one at the bottom, and by the 5 lemma, the arrow the arrow this one induces an isomorphism of the homotypic groups, and so it induces and so it is an isomorphism in the homotypic category. Does this make sense? So spectra are dualizable if and only if they are finite, and there is a way to explicitly describe a dual of a dualizable spectrum. Namely, we take any embedding in some sphere, and then we take the complement if the embedding is nice enough we want to exclude phenomena such as the Horn sphere and so on. If the embedding is nice enough, we take the complement and take the suspension spectrum and shift it, and this is all there is. Are there any questions? Okay. Now, let's remember our goal. Does anyone remember our goal? Why we're doing all this? Well, we've just done it, but we had another more concrete application in mind. Yes, we want to prove this whole thing was needed to prove the Poincare duality. So let's look at another ingredient for the Poincare duality, the Thom isomorphism. Suppose we have a real vector bundle. let's for a okay. Let me first write something on the blackboard or the green board. As, and suppose we have a cohomology theory, which is not just additive but multiplicative. Well, this means the cohomology of every space is a ring, and the relative cohomology is a module over the cohomology of the space. And we will need a few more results. Let's first state and prove the isomorphism theorem, and then we'll see how one can construct multiplicative cohomology theories. So we haven't defined what a multiplicative cohomology theory is. Instead, we want to prove that there's a sensible notion of an orientable bundle, meaning we have the Thom isomorphism. Then we'll look at the ingredients which we need in the proof, and then we'll prove those. Or maybe let me just okay. If there are people in the audience who would rather see the construction of a multiplicative theory first, please let me know. Otherwise, we'll just discuss the Thom isomorphism first, and then proceed to ring spectra and so on. So we want the Thom isomorphism. Okay, so suppose we have a real vector bundle. A vector bundle is orientable if and only if there is a Tom class. The Tom class has basically the same definition as for the usual homology theory. The a Tom class, there could be several. A class is a Tom class if and only if multiplication by this class is an isomorphism between the cohomology of the total space and the cohomology of the total space mod the space of non-zero vectors, or which is the same the cohomology of the discization modulo the spherization, where both are constructed using some metric. It doesn't matter which. Do we have time? Okay. Does this make sense? This is word for word the definition for the this is word for word one of the definitions of orientability for the usual with respect to an ordinary homology theory. And we know that for if H is well, let's recall that if H is an ordinary cohomology theory, then basically there are two cases. either the characteristic is 2, in which case all bundles are orientable, or the characteristic is not 2, then the orientability really doesn't depend on R very much, meaning we get the same answer for all rings which are not of characteristic 2. Well, for other cohomology theories, the answers are more interesting. For example, if we take the real K theory as H, then the orientable bundles are precisely those which have a spin structure. Well, let's not worry about spin structures, but let's have a look at W2. For the usual Eilenberg-MacLane homology, we have E is orientable if and only if W1 of E is 0. And here we have W2. So the condition is sort of similar, but more complicated. And there's a similar condition for the complex K theory. So whether or not the question whether or not a given bundle is orientable in some cases has an answer in terms of the characteristic classes of the bundle. Okay. Yes, well, we know that the cohomology theories are that if we have a spectrum, we have a cohomology theory. Now, as we'll see, if we have a ring spectrum, then we have a multiplicative cohomology theory. So just a spectrum gives us just a cohomology theory. If we want a multiplicative one, we need to assume that the spectrum is multiplicative as well.
What spectrum gives us K-theory?
Well, the K-theory spectrum, which is basically which has basically two components. There's an even component, which is Bu cross Z, and another component which is U. What is U? U is the infinite unitary group. In other words, the direct limit of the unitary groups. Actually, well, here's another another good topic for a talk. The Bott periodicity theorem. We let's look at what it let's say U let's take U to be the limit of U of n. So the K-theory spectrum is the K-theory spectrum is the following spectrum. The even components are Bu cross Z. Well, just Z as a discrete space. And the odd components are U. And now, in order to prove that this is a spectrum, we need to specify a map, and preferably an isomorphism, but not necessarily, from each component to the loop space of the next component. Okay, so which is by definition the same as Bu cross Z. Okay, so this map we have for general reasons. If we have any well, for example, Lie group or something which resembles one, then omega Bg is a homotype equivalent to G. Why? Well, because and why, by the way? At least as topological spaces. There's a multiplication on the left and on the right, and the natural question is whether this is a map of groups. No, not quite. Is this an isomorphism of A-infinity spaces? Yes. What's an A-infinity space? Let's not get into that. Anyway, just as topological spaces. Why do we have that? Why do we have this? GP. Where does this come from? If we are only interested in the topology of both sides and not the group structure. Андрей, откуда у нас такая эквивалентность? Well, both both are homotopy fibers of the map from a point to BG. Why? Well, on the one hand, we have the vibration G goes to EG goes to BG. Well, this is more or less how we define the BG. But on the other hand, we have the path loop vibration, which works for basically every space, not necessarily BG, but works for BG as well. And the space in the middle is homotype equivalent to a point in both cases. Okay. So this we have in general. But the turns out that for the unitary group we also have the other isomorphism, namely the omega of u is the same as bu cross z. Well, the z component is not surprising. The pi naught of omega is the same as pi 1 of u. Well, pi 1 of u is z. Okay, so the z component is not surprising, but bu is surprising, and this is what the Bott periodicity is about. And well, there's another topic which is more somewhat more technical than the complex case, the real Bott periodicity, meaning over R, and the thing is more complicated because here we have period 2, whereas in the real case we have period 8. But there is a more or less straightforward way to reduce this to periodicity for Clifford algebras. And so this is another another good topic for a talk. For Clifford algebras, basically one could just state the classification for the Clifford algebras and present the rest. Okay, so all this was advertisement of one or maybe two topics for talks. Now, where were we? Oh yes, orientability. So the question of whether or not a bundle is orientable with respect to a cohomology theory is meaningful in the sense that the answer is not always the same as the one that we get for in the classical case of the Eilenberg-MacLean cohomology. Okay, and well, for example, if one is interested in index theory, then one does need to know that at least all complex vector bundles are orientable with respect to the complex K theory. Otherwise, the index formula doesn't make any sense. So this thing does have applications. Okay, so we now move on to state and prove the Thom isomorphism theorem. Well, suppose we have a real vector bundle and suppose there's a class okay, real vector bundle. Let's say R is the rank of E. Okay, now we take a multiplicative cohomology theory. Suppose we have a class U. Again, in the relative cohomology of the disk bundle mod the sphere bundle. Suppose we have a U such that for all x in X, such that U restricted to dx sx, where dx is the fiber of the disk bundle over X, and Sx is the fiber of the sphere bundle also over X. Blah blah blah. If we restrict U to the couple dxsx, we get a class in HR dxsx. No surprises there. Well, blah blah blah. Suppose the class is such that when we restrict it to the couple dxsx, it goes to an invertible element of h naught of a point under this series of isomorphisms. Let's look at these isomorphisms. The first one is more or less how we define the relative cohomology groups. The second one is the suspension isomorphism. Well, what about the last one? Well, the last one how do we define the absolute cohomology group starting from the relative, starting from the how do define the non-reduced from reduced? Well, we add an extra point and take the reduced the value of the reduced theory. Okay, so we have an isomorphism between these two, and this is again by definition. And now we recall that our theory is multiplicative. So H naught becomes a ring. So it makes sense whether or not it makes sense to ask whether or not something is invertible in this ring. And then U is a Tom class for E, and as a result, E is orientable. So it's basically the same theorem as for in the classical case, but we replace the usual cohomology with an arbitrary multiplicative cohomology theory. Okay, so let's see. Okay, so we started late, and we basically, if we take that into account, we are on time. Are there any questions?